Hi guys, hope you're all doing okay, still hanging in there with all this online stuff. Hopefully you're keeping on top of everything you need to do when you need to do it and aren't feeling too lost. Don't forget I am available via email. I'm on Zoom during our normal lecture times, Monday, Wednesday, Friday, 9 o'clock, and during my office hours, Tuesday 9:30 till 10:30, Friday 2 till 3. If you want to chat, I also set up a group me and a forum and a Flipgrid. So there's a lot of ways to get in touch. Some are more technological than others. And don't forget, just keep chugging along, working in Alex. That's honestly one of the best ways you're going to get better at this stuff is just practice, practice, practice. Get yourself an open pie as much as you can, especially as we're coming up to the cumulative final exam. You want to just practice anything that you're not instantly doing very quickly. Get yourself the practice at doing those questions quickly and efficiently. Okay, so I'm trying something a little bit different because I had been filming on my phone, which has problems in terms of getting it from my phone to the computer. So I'm going to try talking through the chapter 9 notes on Zoom. Hopefully I don't get interrupted. It's been a little bit tricky trying to get these videos with the whole family at home. It's a lot of noise and distractions going on. So chapter 9 is talking about gases. Okay, so we've already talked about the properties of the three phases of matter, solids, liquids, and gases, and comparing them. And we know gases are much, much less dense. They spread out to fill any available volume, and the volume of a gas will fluctuate with temperature and pressure, and that it's very easy to mix gases with each other unless they react with each other. So as long as they're non-reactive, they will mix completely. They're miscible. So we talked right at the beginning of the semester, that seems a long time ago, about homogeneous mixtures. So a homogeneous mixture is another way of describing a solution. And remember, solutions are not just dissolving solids in liquids. Solids, liquids, and gases can all form solutions. It's really weird to think about solid solutions. We'll get onto that later in chapter 10. But obviously gases can form solutions very readily. So prime example of a solution of gases is air. Most of air is nitrogen, so that would be the solvent. And then there's lots of smaller components of air, like oxygen. That's the big one, right? So oxygen would be a solute in air, argon, carbon dioxide, etc. So how do we measure pressure? The SI units are the Pascal, which is Newton per meter square, because remember, force is pressure over, sorry, pressure is force over area, right? So that's where that comes from. But we use lots of different units for pressure, like bars, atmospheres, etc. So you should be fairly comfortable using dimensional analysis if you have the right conversion factor to convert between those different units. So the behavior of gases empirically is described by the individual gas laws, which are telling us about some very important relationships between pressure, volume, temperature, or number of moles of a gas. So this is like based on common observations, okay? So looking at the relationship between two of those properties while the other properties are fixed. So Boyle's law tells us that volume is inversely proportional to pressure. So if volume goes down, pressure goes up, etc. Charles's law is the one that's telling us that volume is directly proportional to temperature. So if you increase the temperature of the gas, it's going to expand. Avogadro's law tells us that the volume, the space of gas takes up, is directly related to the number of moles of gas there are. Yeah, more moles of gas is going to take up more space. Amonton's law tells us that the pressure exerted by a gas is proportional to its temperature. So we'll explain that one a little bit better later when we look at things on the molecular level, but you are aware that that temperature will cause your tire pressure to go up and down, right? Like when it's really cold and then you get in your car and you're like, oh no, tire pressure's low because of the cold weather, right? Only in Illinois, right? So these individual gas law relationships, you can put them all together to get the ideal gas law. P, V equals N, R, T, okay? You're going to use that a lot in this chapter to solve problems related to the pressure, volume, number of moles, and temperature of a gas. So R is the universal gas constant. It's got many different values depending on what units you're using. In this chapter, we're commonly going to use the 8.314 joules per mole per Kelvin. for our calculations. So once we're familiar with the ideal gas law, we can start bringing that into stoichiometric calculations where we have gaseous reactants or products, okay? So the ideal gas law has that term N in it. N is number of moles, so we can relate pressure, volume, or temperature of a gaseous reactant or product in a chemical reaction to its number of moles, okay? So then it's just like any other moles calculation. If we've got a closed system, then our number of moles of gas are not going anywhere. So very similar to what we did with diluting solutions, you know, M1 V1 equals M2 V2, we can realize the same thing about gases forming a solution. If the number of moles of gas is going to stay the same and the gas constant is going to stay the same, we can make the combined gas law by bringing those two together for the same values of N and R. Similarly, we can substitute in to the ideal gas law to relate density and molar mass to pressure and temperature. So if we have a solution, a mixture of gases, each of those gases we can assign what's called a partial pressure. So that a partial pressure of each individual gas is its contribution to the overall pressure of the mixture. So this is related to the number of moles of each component in that solution. So we define partial pressure as the pressure exerted by one component of the mixture. We sum all the partial pressures up and we will get the total pressure of the mixture. So we use what's called the mole fraction, which tells us the number of moles of the component of the mixture divided by the total number of moles in the entire mixture. If you multiply the total pressure of the gas mixture by the mole fraction of a particular component, you'll get the partial pressure of that particular component. Remember, mole fractions should always add up to 1 because it's a fraction out of 1 of the entire composition of 1 mole, and total pressure should be equal to the sum of all the partial pressures. So once we got a little bit more familiar with those individual gas laws and using the ideal gas law, we want to actually explain why these phenomena occur. So the kinetic molecular theory of gases is how we explain these empirical observations based on thinking about gases on the molecular or particulate level. Okay, so you've got these gas particles, we know they're small and they are moving constantly and randomly. So like in any given direction with varying levels of kinetic energy, which mean they have varying speeds, and the kinetic energy they have is related to the temperature of the gas. So we make a few assumptions, okay, because we've got very small particles spread out over a large volume, because gases are not dense, we're assuming that these gas molecules do not interact with each other in terms of there's no intermolecular forces of attraction between them. And we assume that all collisions with other gas molecules and with the size of any container are elastic, which is where kinetic energy is conserved, right? We don't lose any kinetic energy. So we can explain these individual gas laws using kinetic molecular theory. And it's all to do with how changing a parameter affects the collision frequency and kinetic energy of gas particles, how that affects the pressure, volume, and temperature of a gas. So if we take Boyle's law, which if you remember rightly is that pressure is inversely proportional to volume, if you think about it, if you decrease the volume while keeping the number of moles of gas and the temperature of gas the same, in a smaller volume, there's going to be a higher frequency of collisions with other gas particles and the size of the container. So that is going to increase the pressure of the gas, and vice versa. If you increase the volume, there's going to be less collisions with other gas particles and with the size of the container, so it's going to decrease the pressure. So similarly with Amonton's law, which is telling us that pressure is proportional to temperature, if we increase the temperature, you're increasing the kinetic energy or the speed of the gas particles, so they're moving around more quickly, they're colliding more frequently, and they're colliding with more energy, they have more kinetic energy, so that in turn is going to increase the pressure, providing the number of moles of gas and volume stay the same. If the volume is allowed to change, if you have gas particles with higher kinetic energy, that's going to mean that as you heat a gas up, it's going to have to expand so that it remains at constant pressure, which is Charles's law, volume is proportional to temperature. And of course, how can we forget Avogadro's law, okay, which was that moles of gas is proportionate to volume. Of course, if we add more moles of gas, if pressure and temperature is kept equal, then the volume is going to have to expand to accommodate those number of moles of gas that have increased without changing the pressure. So while we're on the subject of kinetic energy, not all gas particles are going to have the same kinetic energy. There's going to be a distribution, okay? So we usually describe this distribution using the root mean square speed. So we can compare different gases with different like molecular weights, or if we change a condition, how that affects the kinetic energy of the gas particles, like if we increase or decrease the temperature. So the general rules then, if a molecule is heavier, it's going to move more slowly in general. So the distribution of speeds for heavier molecules is lower and a narrower shape. Whereas if you have like smaller, lighter molecules, they can get to these higher speeds. So they have a broad distribution of speeds, and they're able to access higher speeds. So you still see some smaller, lighter molecules traveling at lower speeds, but it's a broad distribution as they can also access the higher speeds. As we increase temperature, we're increasing the general kinetic energy available to the gas molecules. If you heat up the same type of gas at higher temperature, those molecules can get to those higher speeds. So again, that distribution gets higher and broader, okay? So a little bit of a definition for you guys. We talk about diffusion quite often colloquially. In this case, we're talking specifically about the spread of a gas through a medium. So if I sprayed some perfume at the front of the lecture theatre, by considering the kinetic molecular theory, how those gas particles move randomly and constantly, that explains how that perfume spreads throughout the lecture theatre, and eventually you guys like row by row would be able to smell it as the random movement of those particles causes the gas to just keep expanding and expanding. Effusion is when a gas moves through a small opening to a lower pressure area. So if I have a balloon and I make a hole in it, right, in the balloon, the gas is in a high pressure area, but as soon as that hole is available, it's going to want to move into the lower pressure area. So that's what we call effusion. And we can describe the rate of diffusion or the rate of effusion of a gas similarly using Graham's law, which tells us that the rate is proportional to the molecular mass of the gas. So we've done a lot of work talking about the ideal gas law, and it's fantastic. We can use it most of the time. It applies most of the time. But there were some assumptions we made, right? So one of the assumptions we made was that gas molecules are independent of each other. They don't experience any intermolecular attractions to each other. But eventually, at some point, if the pressure's high enough, you're going to force the gas molecules to be close enough that they are going to start to experience intermolecular attractions. So what happens then is that is going to decrease the force of the collisions. So that is going to decrease the pressure below that of what we'd expect for an ideal gas. So another assumption we made was that the volume of the gas molecules is negligible. And actually the ideal gas equation, the V in it, is the free volume. So we've been using the total volume of the container to mean free volume, but actually some of that volume of the container is taken up by gas molecules. So the free volume is the volume of the container minus the volume of the gas molecules. It's slightly smaller. So proportionately, the more space the gas molecules take up, the more the free volume is going to deviate from the volume of the container. So again, we need to make a corrected volume term to acknowledge when a gas is actually taking up a non-negligible amount of space. So we have a corrected pressure term and a corrected volume term, and we substitute those into the ideal gas equation to make the van der Waals equation, which is what we use to model a real gas. And there's constants A and B in the van der Waals equation, which are tabulated that you need to substitute in, and those actually depend on the identity of the gas. Okay, so that is all you need to know about the gas laws. So hope you guys continue to keep well. If you've got any questions, hit me up. Take care, and I'll be back again soon with some chit chat about chapters 10 and 11. Bye.